Okay, hello everybody, what's going on? This is Mohammed. Welcome to another video. In this video, I'm going to show you how to find the Fourier transform of the exponential to the power negative t squared divided by 2. So if you're interested to know the answer, pause this video, give this problem a try, and then keep watching this video for a solution. Okay, so now to find the Fourier transform of e to the power negative t squared divided by 2, let me remind you of the definition of the Fourier transform. Okay, so the Fourier transform of e to negative t squared divided by 2 is nothing but the integral from negative infinity all the way to infinity of the function in the time domain, which is our function e to the power t squared divided by 2, and we need to multiply that by a negative complex exponential e to power minus j omega t dt. Okay, so that's how we find this. Okay, but I wouldn't recommend that you try to evaluate this integral because it's kind of hard to deal with. Okay, but we can do it in a simple way by resorting to the properties of the Fourier transform, and we're going to use here the time differentiation property and also the frequency differentiation property. So let me remind you of those two properties, and then from that we're gonna start. Okay, so we know that if we have a function like x of t in the time domain, that would become what in the frequency domain under Fourier transform? X capital of omega. Now what if we differentiate x of t in the time domain? Okay, what would that give us in the frequency domain? Of course, here we're using what the time differentiation property. The derivative in the time domain would give us j omega multiplied by x capital of omega in the frequency domain. Now, what if we decide to differentiate x of omega in the frequency domain? Okay, so x prime of omega. What would that give us in the time domain? Okay, so that would give us exactly minus jt x of t. Okay, so with that, of course, these two properties, either the time differentiation property or the frequency differentiation property, are easily can be easily proven using the definition of the Fourier transform. Okay, so now let's benefit from that. Okay, so what I'm gonna do now, I will let x of t equals our function, which is e to power minus t squared divided by 2. And then I will differentiate both sides with respect to time. So dx of t by dt would give us what? Would give us minus t e to power minus t squared divided by 2. Now I will take the Fourier transform of both sides. Okay, so we know from the first property, the time differentiation property, this one here, let me use this color. Okay, we know that, yeah, this property here, if we benefit from that, we know that the Fourier transform of both sides here would give us what? Would give us j omega x capital of omega. By the way, x of omega is the thing that we're trying to find here. Okay, so that's going to give us what? Now, if we focus on the right-hand side, it should remind us of the second property. Let me use another color here. This color, for example. This here with negative t and a function of tan would remind us of this property here. So we can benefit from the frequency differentiation property, but we're missing j. So what we do, we're going to multiply by j and divide by j. So this can be rewritten as, okay, minus jt e to negative t squared by 2 divided by a constant, which is what? J. So we have just multiplied by j and divided by j. And that makes the right-hand side, I mean the Fourier transform of the right-hand side, is equal to x prime of omega as per the frequency differentiation property that I have highlighted in yellow above. Okay, x prime of omega divided by j. Now what I will do, I will take x of omega to the other side. Okay, I'm sorry, I'm going to take x of omega to the other side. So that's going to give us what? X prime of omega divided by x of omega. And that would leave us with j times j, which is -1 multiplied by omega, so minus omega. And to find x of omega, we have a differential equation here, okay? And since we have in the denominator x of omega, its derivative in the numerator, so we can benefit from that. We can take the integral of both sides with respect to omega, and that's gonna give us the natural logarithm of x of omega, okay? Would give us what? Would give us the integral of minus omega with respect to omega, which is what? Nothing but minus omega squared divided by 2, of course, plus c. And simply to find x of omega, all we need to do is to take the exponential of both sides. So that's going to give us what? E to negative omega squared divided by 2 plus c, which is equal to e to power c multiplied by e to power negative omega squared divided by 2. Now e to power c would give us another constant. Let's call it c. Okay, so e to power minus like c naught, let's say, whatever, okay? Minus omega squared divided by 2. Of course, we need to use another constant, okay, because e to c is nothing, is not c, is another constant, okay, so we need to, so we use c naught, for example. Now the problem is how to find c naught. So we're almost done, okay, but we need to find or to determine that constant c naught. How do we do this? Okay, now to do this, we're gonna benefit from the fact that x of omega is equal to, let me remind you of the definition of the Fourier transform. X of omega is equal to the integral of, from negative infinity all the way to infinity, of x of t multiplied by e to negative j omega t dt as we did above. Okay, now if you evaluate this integral at omega equals 0, then x of 0 would give us what? Would give us integral from negative infinity all the way to infinity of x of t dt. So if we substitute our x of t function here, that means x of omega is going to give us what? Minus the integral from negative infinity all the way to infinity of e to power minus t squared divided by 2 dt. Now this is a famous integral, and I know that this integral, the value of this integral is equal to the square root of 2 pi, which I'm going to show you how, but I mean, I'm sure this is okay, the value for this integral. Okay, let's finish this, and I'll show you why this integral is equal to the square root of 2 pi. So let's go back here. Okay, so we're gonna substitute this back here, this here. Okay, so I will substitute omega equals 0, so that makes what? That makes c naught e to power minus omega squared divided by 2. I'm sorry, evaluated, x of omega is nothing but x of 0. I'm sorry, I will evaluate that equation at omega equals 0, so that the exponential is going to be equal to 1 because e to 0 is equal to 1, and we're left with c0, which is nothing but the square root of 2 pi. So that makes what? That makes e to negative t squared, okay, divided by 2. The Fourier transform of that is basically equal to the square root of 2 pi e to negative omega squared divided by 2, and that is the solution to our question, okay? So I'll put that in a box, and then I will highlight it with this beautiful color here, okay? Now we're left with one last thing, which is basically how did we decide that x of 0, which is this integral here is equal to the square root of 2 pi. So to do this, okay, so here I'll put a remark. Okay, so this remark will tell us exactly how we determined that, how we found out that the integral from negative infinity all the way to infinity of the exponential of minus t squared divided by 2 dt is equal to the square root of 2 pi. Okay, so the integral from negative infinity all the way to infinity of minus t squared divided by 2 dt can be rewritten as this, okay? So it's the integral from negative infinity all the way to infinity. The exponential, we can write it like this, exponential, okay? I'll take the minus half outside, okay? And the t squared, I will write it as t minus 0 divided by 1 all squared, okay? And dt. And outside, I will divide by the square root of, and I'll tell you why in a minute. Okay, so 2 pi, and then I'll take that one here, this one here, and square it and put it here. So this is 1 squared. So with that, I have divided by the square root of 2 pi. So I have to multiply by square root of 2 pi so that I don't change the whole value, right? Okay. Now I want you to concentrate on this part of the integral. Okay, what does this remind us of? It is basically the Gaussian, the cumulative density function of the Gaussian distribution, right? Okay. So this is basically equal to the area under the PDF, and we know that the area under the PDF is equal to what? Is equal to 1, is always unity. So this whole thing is going to be equal to what? To the square root of 2 pi, okay? This is a Gaussian distribution whose, of course, by the way, this is here is the mean value. So 0 is the mean value. So it's a Gaussian distribution of 0 mean, that's the mean, okay? And this one here is basically equal to the standard deviation. The standard deviation. Of course, which is sigma x, let's say. If we square that, we're going to get the variance, but it's already squared. Okay, so that's the standard deviation, which is 1. If you square it, you're going to get the variance. So the variance is also what? 1. Okay, so 0 mean and unit variance, and the area under this Gaussian PDF is nothing but 1. So we're left with the square root of 2 pi. And that concludes my solution. If you like this video, hit like. And if this is your first time here and you want to know more about brain teasers, riddles, logic puzzles, viral math problems, and all types of mathematics related problems, then start now by subscribing to the channel and clicking the bell so you don't miss anything in the future. Thank you for watching and see you in another video.